Hello and welcome to this lecture. We're going to be studying functions of one real variable in sort of a formal fashion. So far in the previous lectures we've been seeing examples. We saw linear functions of one variable. We saw the mx plus b, which is sort of a straight line function that represented by a straight line. And then we saw some simple example of quadratic and how that has this parabolic type shape, and then this exponential type function, various functions which arose from very practical simple problems. And we saw that these functions were interesting in practice and we wanted to plot them. We saw how the plot looked, and now we're going to sort of formally define what this function is. What is the meaning of what is the definition of a function of one real variable, and then we'll see some examples, and then we'll look at how to think of functions, and then we'll go back to our graphing calculator and plot many more interesting functions and look at how they feel, just to see how different functions behave. Okay, so let's get started. So basically we saw these plots where for a particular value of x we were defining a particular value of y, right? So for every x we could define a y, and then if you connect all those points together we got these nice curves and lines. So I've shown here the red is line, the blue is sort of like this exponential behavior, and the green is sort of like the parabolic quadratic behavior. So we see different types of functions depending on how we assign the value. You get different types of curves on these Cartesian coordinate plane, the xy plane, right? So a function of x is sort of defined in this fashion, as in for every x, every value of x which is called like the independent variable or the input to the function, you have to specify a unique function value or the output from the function. Right? The function takes as input a value x, small x, and that input is a real number, and for every real number x you have to specify what should be the function value, right? So typically this function value is specified as an expression involving x, right? We looked at various things, right? mx plus b, ax square plus bx plus c, 1 plus r raised to the power x. Any sort of formula like that which involves x and some constants and some parameters and all these things, that is how typically a function is specified. Okay, so once you specify a function like that, you can plot the function at the value x, which will be your y coordinate and the x coordinate, and you join all of that, you get this sort of this curve or line. Okay, so I hope this is clear. So it's the function is basically a way in which you specify how an input x is used to generate the output of the function value itself. Now there is this word unique, which I've not spent too much time on. Basically that uniqueness is important. If I give you an x, you should give me a unique value of f of x, or the function evaluated at x, right? You cannot say if I give you an x, the function could be this or that or something like that. It cannot take multiple values. It should be a single value. If I give you an x, you should say one value for the function. Okay, so that uniqueness is one important feature of the definition. We cannot do away with that. Okay, easy enough. So let's see some examples. How do you specify the function value, right? Usually the function value is specified through an expression involving x and some parameters, right? So starting with, interestingly, you can have something called a constant function. For every value of x, my function takes a constant value c. So how will the graph look? It will be one straight line, right? So at the value c, it will be one flat line. Straight line means flat line parallel to the x-axis, right? So every value of x, you get the same value of c. That could be a constant function. Okay, bit boring, but guess what? It's a valid function. For every x, you're specifying a value for the function. Another interesting function we've seen so far is the linear function, mx, right? For every x, you multiply by some slope. Slope could be positive, slope could be negative. Different function characteristics show up, and depending on that, it will have different applications, right, in different use cases. We saw the quadratic function, ax square plus bx plus c. There are 3 parameters here, and then we also saw this exponential compound interest type exponential function, p times 1 plus r raised to the power x. In this case, the x is like the number of terms over which you do compounding. So you have all these expressions. In fact, these are not the only functions. You can do more interesting things. You can combine these functions in very interesting ways to create newer and newer functions. So later on we'll see specific examples. Like for instance, I could add the exponential to the linear function. I could add the constant to the linear function. I could add constant to the exponential function. I can add a quadratic to an exponential. I can also multiply these things, right? So I can multiply linear with quadratic to get cubic functions, and quadratic I can square it and get raised to the power 4, 5, etc. You can get polynomials with arbitrary powers of x. You can get all sorts of functions by combining these functions in interesting ways, and these will show different behavior for x, right? The plot of y versus x will behave in different ways. So we saw these examples. So hopefully this is clear. Coming up with an expression for involving x and parameters to specify the function value seems easy enough, and you can do a whole bunch of functions in this fashion. So later on in this lecture, I'll take you to Desmos and show you how some of these things may look. So it turns out you don't need to really do expression or anything. You can just go to the graph and specify how that function changes with x, sort of draw the graph. Graphically, you can do that, make a few points and then say, this is how the trend of the graph is. You don't have to specify any expression at all. You can just say, this is the function. So let me show how that works. So here's an example, right? You have the x-axis and the y-axis. I just took my pen and then drew like that. Okay, so you can do any other thing also. You would get different functions. I don't know if there is an easy expression involving x for this function. Maybe there is, but it doesn't matter. It's like a lookup table. For every x, I've sort of specified where the function f of x should be. So this is also a good way to think about it. In fact, the abstract correct way to define functions is sort of like this. So you say, the function takes a real number to another real number. I can specify it in any way. It need not be some expression in x, right? I can say, for every x, this is the value. Write one big table. I know it's a very big table, but still, if you do that, that's how the function looks. So is this useful, this kind of, drawing a curve on a graph? So before that, is everything you draw a function? That's also not true. You have to be very, very, very careful. Everything you draw is definitely a relationship between x and y, right? It says for every x where the y can be on that curve, so that defines a relationship. But this one clearly is not a function. Why is this not a function? Because the uniqueness is violated, right? There are many values of x where there could be multiple y, and you don't know which one is there according to this line. So this red line is not really a function. It specifies some complex relationship between x and y, but it's not a function. But notice the difference with the blue line. Anywhere you pick an x, you get a unique y, right? So that part is very important when you draw this line. So any line you draw all over the place is not a function. You can't draw like this column or something all over the place. It has to be like, for every x, it should take only one value of y. As long as you do that, you get a function. Now, this is not a very idle definition. In fact, many functions arise like this. If you remember your science experiments that you would have done, physics experiments particularly, there would have been two things you would have measured, and then you always make a plot, right? Input versus output characteristic, or some characteristic plot. You plot for every x and y, and then try and join those points to get a behavior and a line, and from there you go ahead and predict some relationships and all that. So this is not just an idle thing. Like I mentioned, this is the correct way to intuitively think of a function. Just any line, need not be an algebraic expression involving x, it can be any function like this, and actual experimental data sort of fits this kind of a picture. Okay, so it's not very wrong to think about it. Okay, so this is a good picture to keep in mind when you think of functions. Of course, expressions are also nice. When you can write an expression, it's very nice. But this graphical picture is also very important. Okay, so a little bit of notation and definition. Quite often in books you'll see this kind of notation. You should be able to follow and understand what this notation means. Usually the function itself is denoted by some letter like f here. Okay, my function is f. It could be any other letter also. I'm just picking f. Usually the input to the function is denoted some x or y or some standard variable that we would use. It's going to take a real number x to a real number and the value of the function at x is denoted f of x. Okay, so this notation f of x is a little bit important. It's very, very common. You'll see that this f of x and f. Okay, there is three different notations here, and you should see the difference between all these things. These are not the same. A lot of people will equate f as f of x. They'll say function f of x. Okay, it's okay if you understand that you're making that subtle difference, and so in the notation and the statement, and you're okay with it, it's okay. But f and f of x are not the same, right? F is the entire function, right? The entire graph is f. What is f of x? For an input x, for a particular x, it says what f of x is. Okay, so it's a subtle difference. So that's the difference between f of x and f. So the function f takes value f of x when the input is x. That's the correct way to think of these things. But it's okay. Everybody says the function sin x, the function x squared. That's okay. It's all right. And in usage, people use it interchangeably. But if you want to be technically correct, that is the difference. Okay. Now there is a notation for the real numbers. It's this r written in one, the blackboard type font. This is r written in that different font. That's the notation for all real numbers. And a function f taking a real number to another real number has this other kind of notation. The notation is basically, it will say f colon r to r, the right arrow to r. So this says a function f taking r to r. That's how you read it. The function f from r to r. You can also read it like that, right? So the function f takes a real number to another real number. Okay. Now this sort of tells you that there could be other functions which act on other sets of numbers or other sets of things and takes you to another set. Okay. So general definition of function is like that. A function will take you from one set to another. Okay, that's the general definition. But here in this particular case, we are only interested in real numbers, at least in this course. So we're going to be talking mostly about functions from real numbers to real numbers. A typical notation for function is f, g, h, all that. You can also use alpha, beta, gamma. I mean, anything you want, you can use. But typically we will use this. Typically, this x is the independent variable, f of x is the value taken by it. I've shown you a lot of examples here. Constant function f of x equals c. Constant, see, I'm already using function f of x, right? So the constant, the linear function 3x, quadratic 2x squared minus 30x plus 50, the exponential 1.5 raised to the power x. There are various other examples as well. So this kind of notation you will see in many books, and you should get comfortable with what this notation means. Okay, so now this is the interesting part about functions. Just like you could do operations with numbers to get to more numbers, you can also do operations with functions. You can add functions together, right? After all, a function takes a real number to another real number. You have two functions. You can add the two functions, right? It's very easy. F of x plus g of x, f of x minus g of x. You can multiply the functions, f of x times g of x. You can divide f of x divided by g of x, and you get all sorts of new functions. Notice here I've got x power 10 plus 10 power x. Looks interesting, no? And then you have x power 10 times 10 power x. You can do all sorts of interesting things like this to get various different behaviors. So now why is this important? Because a lot of real life situations, you may get all sorts of shapes, and I want an expression to sort of fit that shape. Okay, so how will I cook up that expression? I will use all sorts of combinations to cook up this expression. Okay, so that's part and parcel of how functions play a crucial role in applications and all that. So different shapes, all of that result from these kind of combinations. Okay, so let's go to this graphing calculator now, and then try and plot some of these things just to see how these functions may look. We go to our favorite graphing calculator. There you go. So let's plot. Let's start. I mean, our favorite plots are always there, the linear function, quadratic function and all that. Let me take this interesting looking function, let's say 2 power x. We have not seen too many of these kind of plots. 2 power x. Okay. So we see that it has this exponential type behavior. I want to add to this another interesting looking function, 2 power minus x. So notice it's sort of like this ulta, right? 2 power x on the negative side is flipped over because I did 2 power minus x. So that's going to happen. Okay. What happens when I add a constant to 2 power x? What will happen if I add 5? The entire graph gets shifted up, right? That's all happens. Let's see if I remove this 5, so maybe I should just say c, okay, and then add a slider. So notice this slider, as I keep adding this constant c, this graph moves up or down. The same behavior. If I make c 0, I would have a certain behavior, that is the 2 power x, right? And then if I move c up and down, notice it goes up. If c goes negative, it goes down. So simple behavior in the combination, right? This is what happens to c. You may say maybe I want to multiply and then check it out, right? So instead of adding c, I may want to multiply c times, so it became 0. So now if I increase this, notice it's just a multiplicative factor, so it changes the nature of the way in which this goes. So if it goes negative, it will go negative like that. When multiplies, something more slightly more interesting happens. I hope you see that. Okay. So now this is 2 power minus x. I might say, let me multiply this with x, right? Or maybe add x to it, right? So notice what happens. Some strange shapes start coming. Maybe I can do cx times thing and then move this around. So notice how wonderfully both the curves are moving around. You can do all sorts of interesting funky tricks here. Maybe I want to multiply these two guys, right? So notice what happened here immediately. Look at the blue curve. So maybe I'll just remove the distracting thing. So C maybe we can keep as 2. So notice how the behavior goes for x times 2 power minus x. So it starts at 0, it goes up and slowly starts coming down in interesting ways, right? So you see, so interesting things happen when you do combinations of various types of functions. So another very interesting combination is higher powers. So notice here you can do x power 3. Okay, so let me remove this distracting guy. So x power 3 has this, look at this behavior. It's got all over the place, and then maybe I can do ax cubed plus bx squared plus cx plus d. Okay, so it wants me to add sliders. I'll add sliders. So notice all these things, and then you have a, look at that behavior. So we got so we saw for square we got one parabola, and when you go to a cubic function, it's got two parabolas, sort of, an inverted, one in one shape, one in the other shape. That's because a went negative. So once a goes negative, that happens. If a is positive, you will get a different behavior. When a goes negative, we'll get a different behavior. And if you change b, these things will move around. If you change d, this thing will just shift up and down. If you change c also, these things will move around in non-trivial ways. So you see that the cubic polynomial does that. Polynomials behave in such wonderful ways. So you can do, like, let's say e times x power 4. So this seems to, let me add a slider for e. Why is it not allowing me to add a slider? Okay. Oh, e is a well-known function, so I shouldn't do e, I'll do f. Then it will ask for a slider. So notice here, if I change f, interestingly, nothing much happens. If I make a different, look at that, interesting stuff keeps happening. So how do I make it even more interesting? I think this way. And then d is not going to do much. I'm trying to see if I can get a interesting sort of behavior here. Let me see. Okay. What does C do? Okay, there you go. So you notice here, I've got a, so I went from power 3 to power 4. Notice what happened when I went from power 3 to power 4. went from 2 to 3. In some cases, I could get, so everything depends on how many times it crosses the x-axis in interesting ways, right? Notice this was power 4 polynomial is crossing the x-axis at 4 points, and it has like this kind of behavior. Okay, so all these things are really, really interesting and intriguing. You can do some curious things like, you can multiply this whole thing by, oh my god, what did I do? Okay, multiply this whole thing by 2 power x. Notice what happened there. Wow, look at that. So you can do all these kind of interesting things there. So you get all sorts of interesting shapes and sizes and behaviors for functions. So I just showed you a few random ways in which I created functions. You can do so much more, right? You can do all sorts of interesting things, and then see how the functions behave on Desmos. So I would encourage you to play with Desmos and literally convince yourself the number of expressions I have are infinite. Any number of expressions I can have, and the type of plots I get are varied, and if I change the constants and change the combinations, I get all sorts of interesting plots. So this is sort of, in one way, it shows you the power of math to model problems, right? So mathematics is so powerful. You can model so many problems, with a simple thing like a function and an expression involving x. Okay, so let's go back to our slide. I think this is the sort of the end of this presentation. Okay, so let's see if now that we have understood the what the various types of functions are, how they look on the graph, we'll go back to our 3 motivating problems, right? You remember the problems we motivated: the shopping problem, the farmer problem, and the bank interest problem. We'll go back to those problems and visualize them on the graph. Okay, so we're going to see graphical solutions for these problems, and that will be the next lecture. Hopefully this lecture gave you an idea of the varied world of functions, so how many different types of functions that are there, and how to write them down in terms of expressions, how to visualize them on the graph, and how these two interplay with each other. Just a brief glimpse of how many possibilities are out there. Okay, thank you very much.